Welcome to Advanced Reverse Engineering. This homework that's due on the 30th. The homework is to take a program and identify the basic blocks and then print them out. We've gone over this. Assume a basic block ends when you reach a return, or a return from interrupt, or a halt, or a condition code jump, or an unconditional jump, or an unconditional loop, or conditional one, or the next block leader. And you discover all the basic block leaders when you encounter the first address that you're given, or you encounter a conditional branch. What happens then? The target of the branch and the address after the branch are both potential leaders. You encounter a jump. What happens there? The target of the jump is a leader. You encounter a call. The target of the call is a leader. Note that call does not stop the basic block. All right. So you'll effectively, you can think of this as making two passes. In the first pass, you're going to find all the leaders. In the second pass, you're going to print the basic blocks. Now, I don't want you to get confused about this. You're not going to make a straight pass through the program. You're going to find them using the algorithm described previously. You're going to start at main, or if there's no main, you're going to start at the entry point, and you're going to, that's going to be your first basic block leader, and from there you're going to look at that basic block and identify any additional basic block leaders you can. Then you will explore those. Now, listen to what I said. You will start at that basic block. In other words, you won't scan through the entire program. You're going to just look for leaders in that first basic block, and they will point you to other basic blocks, and you'll look for leaders in them, etc. Now, because you don't know what all the leaders are yet, you don't actually know what all the basic blocks are going to look like, because you have to terminate early when you encounter a leader. That's what pass 2 will do. All right, so hopefully that makes sense, and you can get this, and you'll be good. Let's talk about concolic execution. This is going to continue off of what we've been talking about previously. The basic idea is identify a set of variables that will be the inputs to your program. Instrument your program to trace modifications to inputs or to trace control flow changes, and then pick some initial values for those inputs. Then you're going to concretely execute the program with that input. Now, what if it's not a program that just takes a fixed set of input? What if it's something that requires continuous input, like it reads the mouse, or it's reading a database, or it's performing some action on streaming data from the web? Then you will have to simulate that, right? That becomes your pool of input. That's you can do that. So you execute the program with that input, and then you symbolically re-execute the program on that trace. Remember, you've instrumented the program, so when you actually did the concrete execution, you were recording the path that the execution took through the program. Okay, so we know what things executed within the program. Imagine you've got a big piece of code, and what you do is every time you reach a basic block, you just record the location of that basic block. And you know that code is going to proceed straight to the block, so that's enough to give you the path through the entire executable. So you record that, and then you symbolically re-execute just on that path. Now remember, with symbolic execution, the problem was the path explosion, right? So I start out, and I represent my inputs symbolically, but then I hit a branch. If this is true, if x is greater than 5, let's say, go do this. If x is less than or equal to 5, go do that. Now I've split my space, and I have to symbolically execute on each of those two conditions. And then I hit a loop, and now I have a lot more conditions, or I hit another if then else, more conditions, and it begins to branch and branch and branch and branch. The path explosion becomes overwhelming. I avoid that here by effectively pruning the tree, as it were. I just have that one path and I then symbolically execute along that one path. So if when I ran it, I took the then branch and the loop ran 4 times, then when I symbolically execute, I only symbolically execute along the then branch and for those 3 executions of the loop. Hope that makes sense. Really reduces the space I have to think about. At the end of this, we'll have some final, potentially, some final path condition. If it's code with no conditionals, why are you doing this? But if it does have conditions in it, at the end you'll reach like the last path condition. So you'll have like if x is greater than 5, go do this, and x was greater than 5, so you went and did that. So then what you'll do is you'll negate that condition. You'll say, what would have happened if x had been less than or equal to 5 at this point? So then you need to figure out how to change all the inputs so that that last condition is negated. You use the satisfiability modulo theories solver like Z3 to do that. That gives you a new set of inputs, and you return to the top and you concretely execute the program on the input values, record the trace, negate the last path condition that you haven't already negated, and you proceed to explore in that way. Now, in the extreme, you're still going to end up with an explosion of iterations, because let's say there are 4 sequential ifs. You're going to look at the true and false of the last one. Let's say that all the ones up to that are true, and then the last one is true or false. That's 2. Now you're going to go through and make the next to last one false, and the last one true or false. And so you can see this could potentially, in sort of a pathological case, it could be in this case like 2 to the number of conditions. In reality, programs tend not to work that way, and usually you're looking for a specific thing as you're doing this. Right? You're looking for a bug or an error or the program to do something else that you want it to do, and you're trying to find a set of inputs that will give you that particular thing. I mean, you could treat this as a path coverage tool, and that's fine, but typically you're looking for something more concrete. How do you instrument a program? I recommend you use Pin. Pin is a dynamic instrumentation tool. It works on Linux, Windows, and Mac. It works pretty much everywhere. It's maintained by Intel, so it's pretty solid. The nice thing about Pin is a lot of instrumentation tools, you have to compile the code with them. You don't need to do that with Pin. You can actually run a target program and instrument that program. So what does concolic execution look like? Well, here's a little example. We've seen this little program, I think, before. Over on the left-hand side, a little piece of C code. The inputs are X and Y. We're going to instrument the code, presume that we've done that. And we're going to initialize by saying X and Y are both 1. And now we're going to do f of 1, 1. We're going to concretely call this with 1, 1 as the arguments. And when that's true, z will be set to twice y, which will be 2. X will be checked against 100,000. X is 1, so that does not pass. So we don't do the if, and we're done. Now we have a path, right? And so we symbolically execute. And the first thing was to say z gets twice y. And the next thing was we didn't take that branch, so we have the condition x is not equal to 100,000, and that's our symbolic execution. So now we need to negate that last condition. So we say not x not 100,000, which means x is 100,000. We call the SMT solver, and it comes back and says yes, x is 100,000 and y is 1. And then we execute on 100,001. So when we do this, z is going to get twice y, so z will be 2. X is in fact equal to 100,000, so that second if goes, and we go into the then part. We now compare x and z. So we ask, is 100,000 less than 2? And the answer is no, so we don't do the inner if. And we're done. So now we can symbolically execute. Z gets twice Y. The path conditions are now X is equal to 100,000 and Z is greater than or equal to Z. No, sorry, X is greater than or equal to Z. Now, that's the last path condition, so we negate it. And the negation, we say not X greater than or equal to Z, or X greater than or equal to Y. And again, SMT solver is going to figure that out for us and give us some new stuff. And so now it gives us the new X and Y. X is 100,000 and Y is 500,001. Sure, it's going to give you something, right? So we execute. Z gets to be twice Y, which makes it 1,000,002. X is 100,000. We ask the question, is 100,000 less than 1,000,002? Yes, it is. So the inner if fires as well. We reach the assert 0 and we have a failure. So now both have taken and we've discovered the error in the program. So that's all well and good, but we need to automate this because doing this by hand would be painful. The Concolic execution process looks like this. In step 0, you instrument the program and pick any valid inputs. And you establish experimental control so that if you were to run the program several times, you would expect within a reasonable amount of variation to get the same results. If that makes sense, right? When you run an experiment, there's always going to be some uncontrolled source of variation. But here we want to minimize that or make that work in the way we want. Maybe we have to seed random number generators the same way every time so that it evolves the same way. Maybe we need to explicitly pace the execution so that time is less of a factor. This can be quite hard. Okay, this can be quite hard, but it can be done. So then in step 1, we run the instrumented program with the specified inputs and we record the trace. That takes us to step 2. We symbolically execute the recorded program and record the path conditions. Now here's where we might stop. If we've reached the desired halting criteria, we stop. Otherwise, we negate the last path condition, solve for plausible new input values, and then we repeat. Let me go around the circle again. So for Concolic execution to work, we need a few things. We need a way to instrument the program. We need to run the instrumented program with the specified inputs and record the trace. We need to symbolically execute the recorded program trace and path conditions. We need to negate the last path condition and solve for input values. And to do all those things, we have tools. So Pin will let us instrument the program and it will record the traces. Capstone and the program semantics will let us symbolically execute the program trace. Z3 will let us negate a path condition and solve for new input values. Only thing we haven't got right now is a nice semantics. The semantics Capstone gives us, these values are modified, these are read. That is in fact a semantics. It's just not sufficient to do this. And that takes us to Triton. So Triton bills itself as a dynamic binary analysis and invents an acronym for that framework, DBA. When I see DBA, I think doing business as, but it's the dynamic binary analysis framework. It provides internal components like symbolic execution, a taint engine. We didn't have time to get into taint analysis, dynamic taint analysis in the class. Sorry, it's not that challenging. I think you can read up on it on your own. It's another fundamental technique. AST, or abstract syntax tree representations of the x86, x86-64, and the ARM instruction set architectures. SMT simplification, an SMT solver interface, and of course Python bindings, because everything has to have Python bindings. If your dog doesn't have Python bindings, get a new dog. No, don't get a new dog. You should always love your dog. So there are the pieces. The interesting part to us is that AST representation of semantics, because that was the piece that was missing from the other things we needed in order to do Concolic execution. And Triton uses capstone, pin, and Z3. No surprise there. Here's sort of the Triton flow. I put this up here because they make a big deal of it, but you can sort of see how all the pieces fit together in here. And you can see symbolic execution over there on the right. You see concrete execution over on the right, and you can tell that those two together mean we're going to be doing concolic execution. And you can see this SMT solver hanging off of that, a disassembler, etc. How do I install Triton? Well, it's not too bad, depending. Sometimes Triton moves forward and you have to update other stuff on your machine. Sometimes that stuff moves forward and then it becomes a problem until Triton catches up. Maybe you have to install an older version of something. Right now we seem to be in a sweet spot because when I did this I had no trouble. So you install some prerequisites. Some of these are already installed. Some of them you may need. Z3, libz3dev, that's just getting you the SMT solver. Boost is a C++ library that's almost entirely template metaprogramming. It's really a neat thing to take a look at if you like C++ and you're curious about how you can do most of your work in the compiler. Have a look at it. CMake is the build tool. Python dev is Python 3, just points to the correct Python 3 libraries. libcapstone dev is the development library for Capstone. Python 3 torch and Python 3 numpy you're probably familiar with from your data science classes. Once you have all of those, you can clone the Triton repository. And I like to do out of source builds. So I make a build directory and go into that build directory, and then I use cmake ... That's a way of doing out of source builds. Then do make j2, and this will take a while. So you can take your dog for a walk, whatever you want to do. You can watch some YouTube videos on Triton. Then do sudo make install. That will install everything for you to use, including the Python libraries, and then you'll be ready to go. Now, how do I use Triton? Well, here's how you use some of the other tools we've looked at, and I point this out because it's going to be relevant. So from ELF tools, we're going to import ELF file. We're going to go ahead and open up a file as a binary. We're going to wrap an ELF file around it, get the text section. We're going to get the entry point of the text section. We can get the data from the text section, and there we go. We're ready to begin to analyze it. And we could use Capstone to do that. So from Capstone, we'll import the usual suspects, and I'll create a little Capstone instance with the correct architecture and the correct mode, and then I can define a little function, and that I'll call it capget. I'll give it an address, and that will fetch an instruction from me from the text section. So remember, data I got earlier, that's my text data. Adder I got earlier, that's my argument to this function. Start I got earlier, that's the address of the start of the text section. And so you can see what I do here. I go ahead and do a CS disasm, and I've got to provide it with two things: a byte string and the address of the first byte of that byte string. And so I slice the data to do that. I go and take, since I know it starts at start, and I wanted an adder, which is presumably after start, I subtract. And I take all the bytes from that point forward, and then I give it the address of those. This is pretty efficient. I'm taking a sort of forward slice, so I can do that in place. I just move a pointer to point later in a buffer. So this is actually a pretty efficient little function. Then I go and call the generator that's returned by disasm and get the next instruction. And building a new generator each time is not ridiculously expensive. So I do that and I return the resulting instruction. So now I have capget, and I call capget with the entry point, and I get back the NBR64 that's there. I hope this all makes sense to you. You've been doing this for a while now. That should all be perfectly reasonable and sensible. Now, let's talk about Triton. So from Triton, we're going to import a few things. We're going to import Triton context. we're going to import arch, which is the architecture, and mode, which is just what it is in Capstone, and something called AST representation. That's going to give us our semantics. So I'm going to make a Triton context. I'm going to set the architecture to x86 64. I'm going to set the mode to aligned memory. Now, what's going on there? Well, it turns out memory alignment is just a useful, helpful thing to assume. And we're going to do that for this. You should, if you're curious about that, you should read about it and decide whether you want to do that or not. We're going to set the representation mode to Python, and we'll see that in just a moment. And now I'm going to build that same function, but I'm going to build it in Triton. So I'm going to go ahead and import instruction from Triton, and I'm going to make a function called try_get. I'm going to give it an address, and it's going to give me back the instruction at that address. So what I'll do is I'll make an instruction instance. I'll figure out the offset to the thing I want, address minus start, same as before. I'll slice data, but notice I'm slicing out 15 bytes. Why 15 bytes? To set the opcode? Well, 15 is the largest instruction on the processor. If you go more than 15 bytes, you trigger a processor exception. Theoretically, you can have more because of prefixes. In reality, you can't. Then I go ahead and set the address, and then I call processing to fill all the details in for that instruction, and then I return it. So TI is a little Triton instruction, and so when I call try_get and give it the entry point, I get back the same instruction in BR64, that initial no-op that used by the branch protection system. Great. So it seems to be doing, up here I got a CS capstone instruction, and it gave me some information. So far Triton seems to give me less information when I print it out. Well, that information is all available. I can get the opcode, and that gives me back a byte string. And you'll see it's not 15, it's reduced it to just the 4 it needed. I can get the address, and I'll convert it to hex, and there it is. I can get the next address. Ooh, this is neat, right? So in Capstone, what you may have done to get the next address is added the instruction length to the instruction's address. Here we can just call get next address, and it will do that for you. I can ask if it's a branch, and I can ask what its operands are. And NBR64 doesn't have any operands. So far, not much has changed. Interface is slightly different. We shouldn't necessarily expect a lot to change, because under the hood, Triton is in fact using Capstone. But, at least we can get the same kind of information. I can go and get the registers that are written, or I can get the registers that are read. And you'll see here, it tells me that for NBR64, instead of getting back an empty set, which I might get from Capstone, I'm told RIP, which is a 64-bit register, is in fact written, and it's written with 2F94. That's going to be the next address. That's pretty neat. But more significantly, I can get semantics. So if I go ask what are the semantics of NBR64, it says it advances the program counter. And that's true. That's interesting. But notice what it does. It tells me that ref1 is this. So ref1 is a new value for RIP. This is actually giving me back the information in static single assignment form. Instead of using something more transparent like saying EIP sub 1, it happens to be using ref sub 1, but the same kind of thing is happening here. It's converting everything into static single assignment. And also, this is executable Python code. That's neat. I could just run that. We can look at some more complex semantics. So I'll get from a different location, and in this case, I get back call, keyword, pointer, and it's an RIP relative address that I'm going to be calling. And I can then ask Triton for the symbolic expressions that make that up. And you'll notice over on the left-hand side here, bunch of refs, right? Because it's put it in static single assignment form. And those are these specify a lot of different information. They mainly are telling me, here's what happens with each of the registers that gets modified. Here's what happens with each of the other pieces. So, again, this sort of also hints at why I need a Triton context. I need a Triton context to tell me what those little things all mean. I can also get the semantics in SMT-lib form if I want that. And there we go. This will let me put them straight into a satisfiability modular theorems prover and get a result. And it's nice that there's this standard lib, that the standard language that lets me do that. Here's a slightly simpler example, maybe. Exclusive ORing ESI with itself. And you can see that, again, it's creating all these intermediates. So this first one, and this is in a Lisp-like syntax. So if you're not familiar with Lisp, you sort of have to read it from the inside out. So here I have a 32-bit bit vector, same 32-bit bit vector. I am exclusive ORing 2-bit vectors. One with itself, that's really going to give me a 0. It hasn't necessarily figured that out yet, but that's okay. And then I'm going to 0 extend that, and then I'm going to store that over here in some other bit vector that's 64 bits, and that's going to be my ref29, which in this case is going to be my new value for ESI. And then I set the carry flag and the overflow flag. The parity flag is always a complex mess. The sign flag, the 0 flag, and the program counter. And those are all done with these references because for example, ref 31 is never going to change. That's what the static single assignment stuff is for. All right, and there you go. There's the piece that does the exclusive OR, and I'm just pointing out that dealing with semantics can be hard. All right, so that's the end of my little quick discussion of Triton for now. Let's talk about SimCC. That's a different kind of beast. Triton can be complicated, but it's a really nice general purpose tool. You could have built all the stuff that you built over the semester using Triton, which would in turn have used Capstone. And that might have been helpful to you because then you could have gotten program semantics, but maybe you weren't ready for that just yet. Now, the compiler has access to everything we need. In fact, it may have better access. It doesn't, it has the true semantics, you might say. It actually knows what's going on. We have to sort of guess. So it can instrument the code as it compiles it, and it can get its semantics out of the RTL that's generated by the compiler. Wow. That hints that maybe we could build a system like this, a Concolic execution system, straight in the compiler if we have source code for the thing we want to analyze. And you can. In fact, that would be SimCC. And their mantra was don't interpret, compile. Interpretation is slower than compilation. Compile symbolic execution capabilities straight into the binary. Note what they're saying here. Compile symbolic execution capabilities straight into the binary. So as you're executing the code, you're also symbolically executing, and that can be neat. So here's some of their slides. We have a target program that's over there, written in their RTL, and we go ahead and modify that to include some other stuff. And we would do that with something like CLE, S2E, or Anger, which you should look up. Anger is a really neat little tool, and that requires that we make modifications to this, and we have to do that a bunch of different times. Their approach directly modifies their RTL and adds in the pieces that it needs in order to do symbolic execution. So you can see symbolic get parameter expression, build integer, build shift left, build equal. It's going to do all the different little pieces symbolically. It's going to actually output the code, and there you go. So we do all that. Compiler pass and runtime library. The pass inserts the calls into the library at compile time. and then it builds up symbolic expressions, and then calls a solver, and it could call Z3. So, excuse me. They use Clang, so you support C and C++. Might be able to support Rust with a little bit of work. Simple backend is a wrapper around Z3. There's our friend Z3 again. And what is QSIM? QSIM is a Concolic execution engine for hybrid fuzzing. Another one. That's interesting. Why would they build a backend for this other tool called QSIM? Reuse the expressions and the solver infrastructure from QSIM, but not the instrumentation. What's going on there? Well, to figure that out, we need to take a look at QSIM. QSIM is something that I think is pretty neat, as you can tell from the slide. It instruments binary programs at runtime using pin and ptrace. Now, we talked about how ptrace works and how to enable it if you need to. This is way faster than interpreting the code. Okay? Way faster. And you can go and find that online. There's a URL for it. And there's some papers written about it. Triton interprets the code. QSIM rewrites the code at runtime. And SimCC compiles itself into the code. 3 different approaches. And it really depends upon what you need as to which one you want to use. Okay? I don't have source code. I have a binary. How can I use something that deals with source code? Maybe Rose will help you. So Rose is a compiler. It accepts stuff in one form and compiles it to a different form. So it can translate between programming languages, for instance. The Docker image for it available. I'm not going to get into it here. It's a complex beastie, and you are welcome to have a look. Go and grab the... it's very difficult to build, by the way, but go and grab the Docker image, and you should be good to go. There's a Docker container for SimCC as well, so you can go grab that and play with that. I'll give you a little script over on the right-hand side for getting it to run. And you may want to install some stuff inside the Docker container that will help. And there are some stuff that can help, like BSD main utils, less Vim, XXD, things like that you might want. If you're not a Vim person, pick your editor of choice. And so here's an example of how you might use it. You can use Sim++ to build, and then you can just run stuff and see what you get. All right. Whew, that brings us to the end. Let's talk about some bonus homework that you can do. The homework is due at the same time the exam is. Bonus homework number 1 is to take your blocks program and write out an if-then-else or a sequence for each node in the program. So if you'll go back and look at how the structure theorem worked, you'll see the first thing we did was take each line and create either a sequence or an if-then-else out of it. And that's what you're going to do here, and you're going to name it flow. And what's that going to look like? It's going to look like this right here. So on the left-hand side is an if-then-else, and you can see we have a predicate, which is a basic block, ending in this case in a conditional. And so when that jump is taken, that's the then part. When that jump is not taken, that's the else part. And you see what we do is we set the label appropriately. For the sequence, same thing. Basic block is there, and then the label indicates where you go next. Okay, now I recommend you keep track of the nesting depth and indent your code properly. And you may say, Stacy, why? This is going to indent once. We'll get to that in a minute. Also, it's worth noting that that predicate has side effects, and that's okay. Don't worry about the side effects. So be sure your label settings are correct. You should be pointing to the next instruction to execute, or the next basic block to execute. And don't worry about the side effects from the predicate for this exercise. But I want you to ask yourself, should you? What could there be a problem out of that? Think about that for just a little bit. Bonus homework number 2. That's going to take the stuff you just did, and now it's going to try to do reductions. So whenever you have a label that's referenced only once and exactly once, you're going to replace that. Okay? And that's going to result in stuff that looks like what you see over on the right-hand side. Okay? And here you see I have had to do a little bit of indent the nesting depth a little bit, so it's worth keeping track of that. And notice that my then part is no longer just a label setting, it's now another if then else. And the else part is no longer just a label setting, it's now a little sequence. So you should be able to nest these structures. If you build your code that way, it'll really help. So you'll write out the address of the structure followed by the structure. And notice here we have a common label at the end of this. Both the then and else part end with the same label. We can factor that out, and you should. So I want you to factor that label out. So now, instead of the then part being an if then else, the then part is now a sequence consisting of an if then else and a label setting. Turns out that's also a loop. Now, when you have this specific form of loop, just this form, I have a structure. That structure is an if then else. At the end of the then part, I refer to myself. In that case, I want you to convert it to a loop. I hope I was very specific, just that one case. What about the else part? What if the else part referred to itself? Don't do that, because in that case you have to negate the predicate, and I don't want you to try to fool with that. So when we have that case up there, then you will rewrite it. So notice that what's happened is on the true branch we do 3 and then we go back to 1, which assuming that is, and then on the false branch we do 4 and set level to 5. You'd wind up with that structure at the bottom, and there you go, because we don't want to have to negate the predicate. That looks like this. So now I have a while, I check the predicate, I have a do. The do is now just that if then else. That label setting is gone. It was eliminated when I converted to an if then else. Hope that makes sense. Whew. Bonus homework number 3. So this is a little different. In case you don't want to do all that programming, let's find something that's sort of less programmy for you to do. So an opaque predicate is a predicate for which the true or false branch is always taken regardless of the input. It looks like it's a conditional, but it's really not. It's like asking, well, if 1 is less than 2, then do this, otherwise do that. And you're like, well, it's always less than 2. Well, there you go. So an example is that code down there. So I go ahead and exclusive OR EAX and RSI, and then I jump if not overflow to skip, and I jump over the code. Well, the XOR instruction always clears the overflow flag, therefore that jump will never be taken. But it looks like it might be. You're being fooled. So what about the code over on the right hand side? Is that an opaque predicate? Stuff going on there. How would you figure that out? Well, you could write it in the static single assignment form. You could try to back substitute. You could try to slice. There's a bunch of different techniques you've learned that you might try to apply to that, even symbolic execution. What you're going to do for this one is write a Python program using Z3 to determine if the fragmented right is an opaque predicate. I said this was less programmy. You can do that at the prompt, right? You can fire up Python and start typing stuff at the prompt to test that out. And then once you're happy, you can record your Python history in a file and you're in good shape. So what you'll do is you'll create constraints for each line based on that line's semantics. Now, for that to work properly, you probably should be putting things in static single assignment form. That's what I'd recommend. Now, what do you need to consider for that increment line? Do I have to keep track of RAX, or do I have to keep track of all the flags as well. Well, have a look at it. You might decide what's live and what's not live, and that might inform your decision about what you have to keep track of. So, when you're done, I want you to print out your constraints, and then I want you to tell me if it's opaque or not opaque. And if you're curious about how I test that with the SMT solver, you can directly check for SAT at the end of that. So, again, there are some techniques we talked about that will help you. Don't use capstone here since it won't give you enough semantic information. You don't need to disassemble the code. You don't need to put this in a file and do all that. I don't expect your program to accept this as input and then manipulate it. I expect you to, by hand, create the constraints you need. And that's what I want you to do. All right. If you want to know exactly what each instruction does, you can go look it up on Felix Claudia's website. You can look at the Intel manuals. You can get P code from Ghidra. You can go to Triton and get their semantics. Whatever. I think you can figure this out. Next class, you get the final exam. So when you have questions, let me know. Until then, take care.